Welcome back to ELE 115. This will be lecture 5, and we've talked about resistive circuits. I thought we'd do a combination circuit example just to, get that back into our minds. And so what I've provided here is a combination circuit. Combination circuits include series circuits as well as parallel circuits. The particular one I chose here, you could look at this from a high level and say, well, there's a parallel circuit right there with R4, 5, and 6. There's a parallel circuit with R2 and R3. And so one could redraw this circuit in the following way. And of course, this would be R1. This we could call R23 if you like, and this one we could call R456. And this is 5K. And this one here is equal to R2 in parallel with R3. And this one's equal to R4 in parallel with R5, in parallel with R6. So, maybe we can, excuse my reshuffling here, maybe we can implement some sort of zoom action here. And
Yep.
there goes the highlighter. Let's see what we can spin around here. How high we can get this thing off the ground. Maybe we could even make this so it can see an entire page. I don't know. Yeah, that's getting there, huh? Just humor me on. Alright. And that looks pretty good. So there's our first page. So yeah, we just visualized these three things as three resistors and made them there. So let's talk about a couple of things. One, you see the symbol here called ground, and people talk about ground, and it has a lot of implications. For our schematics, ground is nothing more than a reference point. In real life, ground may or may not be connected to soil or in the earth. All right. In electrical power distribution, it typically is connected to what's called an earth ground. And in different drawing regimes, you may have different symbols for ground. You may see something like this. I think this may come from European circuits. I don't know. That's a ground. And of course, I think you've already seen in LT Spice, they use this. Other people use that, although this could mean a negative power supply as well. So when I'm talking about ground and I have control over it, I like to use this symbol. And let's make some modifications to our circuit. Let's call this node A. Let's call this node, there we go again. Let's call this node B. So obviously node B includes all this wire here. And this we'll call node C, and that includes, you know, from here up and down, this thing, and that thing, right? And then we have this node here is ground, okay? If you want to, we already have a symbol on it, but if you wanted to, you could say something like ground and put it on there. Now we measure voltages. For instance, the voltage A equals the voltage from, I'm going a letter ahead, from A, you know, node A to ground. Whereas, and so that one letter type designations indicate a voltage taken to a common reference point. In most schematics, they'll use ground, but somewhere on your schematic, if voltages are given and you're doing troubleshooting, you might want to see that if there's a place on the schematic, some note that says all voltages referenced to test point 123 or something like that. You know, you want to check for that. But typically, voltages are measured. You know, voltages with a single letter are measured to ground. If I were to do something like VAB, that would be the voltage from node A to node B. If you already know this, you know, it's fine. I'm sorry. I just want to make sure that we are basic vernacular, and you know, when we're in lab, that we're able to use that, you know, the common vernacular. This is the way most people describe these voltages. Now, the complicated thing about combination circuits, you know, we can do some simplifying here, and we will. Well, I'll get onto that in the next page. But you can see that if you really want to understand every possible thing about this circuit, you're going to want VR1, which is the same thing as VA to B. And you're going to want VR2 and VR3. Now they're in parallel. Parallel circuits have one voltage and multiple currents. So the only voltage you need here is VBC, and that takes care of, you know, VBC. That takes care of, that's the same as VR2 and VR3. And we have the same situation, a similar situation here with VR4, VR5, and VR6. They're all equal because they're in a parallel circuit with only two nodes. They have individual currents. There'll be an IR4, an IR5, and an IR6. But VC, or VC ground, if you wanted to call it that, VR4, VR5, VR6 are all equal to VC with respect to ground. Okay, so I'm going to move this over to another page. And this will be ELE 115. Lecture 5, 2 of whatever. All right, so now, if you look at the circuit we had here, we have some jobs to do. We know that R1 is equal to 5K. And then we have that R23 is equal to 5K in parallel with, no, I'm sorry, not 5K. It's equal to 9K in parallel with 11.25K. So here's 9K in parallel with 11.25K. All right. Let's consider our notes from lecture 3 regarding parallel circuits. In each parallel circuit, one voltage, multiple currents, and here are our formulas. Now, when we have, a lot of resistors in parallel that are different, we can use R parallel equals 1 over R1 plus 1 over R2 plus 1 over R3. We can use, if we have two resistors, we can use product over the sum. The product of the two resistors over the sum of the two resistors. And if we had n equal resistors, we just take that value and divide it by n. The other thing I want to mention is, if you like it, I tend to do things this way. This product over the sum, it works if you have, say 4 resistors. You could, in parallel, you could take the first two, take product over the sum, use that value and do product over the sum with a third, and use that value and do product over the sum with the fourth. Just so you know. But let's do our let's do our big formula here. So hopefully this will be clear enough to see it. If you have a TI-30, which is a great calculator. In fact, you know what? I'll do. Do I have my TI-30 here? That's the question. And I do. Let's see if that shows up in the light well enough. I'll put it down here just so you can see this particular equation. I have this in one of the algebraic modes there. So now product over the sum is pretty easy. If I have k ohm resistors, I could carry the k through, but I could just, I can actually forget the k because the answer is going to be in k ohms. So I can take 9 times 11.25 and divide it by the quantity 9 plus 11.25, end of quantity, and hit enter. So let me just show you that equation again. You can see it. So I got, one number, which is 9 in this case, times 11.25 divided by the quantity 9 plus 11.25, end of quantity. I hit enter, and I get 5. So this is going to be 5 k ohms. So, this is equal to, 9k times 11.25 k ohms over 9 k ohms plus 11.25 k ohms. And we know from the calculator that equals 5 k ohms. Okay? Now let's look at R456. We could do product over the sum, if you like. Where we're looking at 10k, 15k, and 30k. So let's write this equation out. We got these guys are equal to 10k in parallel with 15k in parallel with 30k. All right. So that is actually equal to 1 over the quantity 1 over 10k plus the quantity 1 over 15k plus the quantity 1 over 30k. Sorry about the shadows there. So that's R456. All right. Now you can each of we could play some games here. I made this come out nicely, but let's see if we can do that one on here. I'm going to clear things. I'll do it on both calculators so you can see the equation. But I'm going to do 1 divided by a giant quantity, because this whole bottom here has to be in its own quantity, right? You can't divide, by parts of these. They have to be added together and then divided into 1. So let's see what I got. I've got 1 divided by the quantity, and let's do our first one. 1 divided by 10. Now they're all K, so I'm going to be sleazy here and not put the K's in. But if they weren't that way, you'd have to put in the numbers exactly as they are. So bear that in mind. Now I can add another quantity here, 1 divided by 15, and end that quantity. Then I can say plus another quantity, 1 divided by 30, end that quantity, and then end the denominator and hit enter, and lo and behold, I get 5K. So as you can tell, I made this thing come out the way I wanted it. So now our circuit is a series circuit. Well, at least for analysis sake, I have 12 volts, and I have my reference point. Again, that's all ground is for us most of the time. If I had a system here and it was connected, say, to an earth ground or a water pipe or something like that, and I had another system over here and it were connected to an earth ground or a water pipe, and I wanted to measure things between them, then I'd have to take that into account. So this is R1, which is 5K. This is R23, right? R2 is in parallel with R3 there, and it's equal to 5K. And this is R456, which also came out to be 5K. Now, as we learned in lecture 4, under the voltage divider rule, the voltage across each resistor is proportional to the total resistance. Well, this guy's 1/3 of the total resistance, this guy's 1/3 of the total resistance, and this guy's 1/3 of the total resistance. So the voltage, by inspection, you can tell the voltage across each of these resistors is going to be 1/3 of 12 volts, or 4 volts. So we know that we're going to have a voltage drop here of 4 volts. We're going to have a voltage drop here of 4 volts, and we're going to have a voltage drop here of 4 volts, and of course we'll have our current. I guess I should have done those in green. Haven't we been doing voltages in green? Let's see if I can get this to... All right. So by the voltage divider rule, we can tell those are all equal voltages, and they have to add up to 12 volts by Kirchhoff's voltage law. So 12 divided by 3, that's 4. Now we do have a current flowing over here. Right? And this is I total. And now we can use Ohm's law to find I total. And to find I, we cover over I, and we get V over R. So we know I total is equal to V total over R total. Well, what's R total? We now have a series circuit. And R total is equal to R1 plus R23 plus R456. And so R total essentially is 3 times 5, or 15 k ohms. Okay, so I total is equal to V total, which is 12 volts, divided by 15 k ohms. And let's see what that looks like. Try to get this in the best visible thing. So I have, that's too many. So I have, let me clear it out. I have 12 volts divided by 15, and I go second EE. There's a purple EE right there, and that's positive 3 because they're kilo ohms. And the answer is, I'm using engineering notation, 800 EE minus 6. So that's equal to 800 times 10 to the minus 6 amperes. Okay? And so we can say that I total is equal to 800. Now 10 to the minus 6 is millionths or micro, so that's micro amperes. Okay? Okay, great. So now we know our I total. We can, now theoretically, if I multiply I total by 5K, I should get 4 volts. So let's try that for a second. Let's take this guy here and multiply this times 5 EE3, that would be 5 k ohms. And I get 20,000 here or something, huh? Something didn't come out right there. Let's go back and do that again. I've got 800 second EE minus 6. That's 800 microamps times 5 EE3 and I get 4. Something, I must have touched another button there. So you can see the answer is 4. So VR1 is equal to, actually let me write something here so make it very obvious for you. I don't somebody picks up these notes. So we know that R1, I'll just say in our case, R1 is equal to R23 is equal to R456. They're all equal to 5K ohms. So VR1, because it's a series circuit, right? I'll just say series circuit. So VR1 equals VR23, and that's equal to VR456, because there's only one current in a series circuit, and if all my resistors are 5K, that same current times 5K, it's always going to come out to 4 volts. So that's going to be equal to IT times 5K and that's equal to 4 volts. Okay? Now, we basically have taken care of the high level view. Now we know that this voltage here is 4 volts, the VAB. VBC is 4 volts, and VC to ground is 4 volts. So now I can go take a look at the individual circuits, and I don't have to look at R1 because we already know it has 800 milliamps there. We know it has 4 volts across it and that it's 5K, so that's done. But let's look at VBC, and so let's look at R2 and R3. So I'll take this off. And so let's look at VBC, or I got a better idea. Let's look at we'll look at this part. This is R2, and it's 9K, and this is R3, and it's 11.25K. And we know, all right, we already know that we have 4 volts across here. So what's left to learn is we would like to learn this current. I would call it IR2, and we'd like to learn this current, which I will call IR3. Again, Ohm's law takes care of this for us. We put our little diamond up here, or our triangle up here. V, I, R. Okay, and we want to know I, so we cover it over, and it's V over R. So IR2 is going to be equal to VR2, divided by R2. And that's going to be equal to 4 volts divided by 9K ohms. And let's see what that gives us. All right, we're back up here now. And we'll take, put this on, we'll clear this out, and we'll say 4 divided by 9 EE3. And we're going to get 444.44. I'll say approximately. Here, how's that? We're going to get 444.44. Now, we don't have this kind of precision. Microamps, because it comes out to 10 to the minus 6. Let's see, but that's a minus 0.06 right there. Okay, so that's IR2, and then IR3 will be VR3 divided by R3, okay, and that's equal to 4 volts. Again, it's a parallel circuit, so the voltage across all the resistors is equal. There's just 2 nodes here, and we're going to divide that by 11.25 k ohms, and I'm pretty sure we're going to get another thing. Now, we all know Kirchhoff's current law. What do we have coming into here? I total is coming into here, and it's equal to 800 microamperes. Okay? So if I got 800 microamps coming in and I got 444.44 microamps going here, then I got to have something like, 356 microamps going down through here, because whatever comes into this node right here has got to leave it. We can't stack up current out of this node, and we can't create current out of nothing at this node. So 800 goes in, I lose 444 and change over here. I've got to get 355 and change over here. So let's take a look at what we've got. We're going to clear, we'll clear that guy out, and we will say 4 volts divided by 11.25 EE3, because it's K ohms. We hit enter, and look at that. We get 355.55. We'll call it, and you know what we'll do? We're going to call it 355.56. Again, this is like approximately equal microamps. And now IR2 plus IR3 should equal I total by Kirchhoff's current law. All right, let's see how we do. So I've got I'm going to use my inexact numbers here. I'm going to say 444.44 plus 355.56. These are both microamps, equals 800. Oh, I'm sorry. There we go. There's 444.44 of something, and there's 355. So 444.44 plus 355.56. Okay, gives me 800. Now these are microamps, obviously. Okay, so this checks out. All right, Kirchhoff's current law checks out. If we go on with this thing, okay, let's look at this guy here. Let's look at now our resistors here were 10K, 15K, and 30K. And we know that from our previous analysis, we have 4 volts across here, and what's coming in here is IT equals 800 microamps. All right. So now we have IR4, we have IR5, I think that's readable, and we have IR6. Okay. I should have gotten my thinner red pen, but I think you can read these, and I'll be posting these notes as well. So let's go get our currents here. We know we only have one voltage, so we can look at this thing and we can say IR4, again by Ohm's law, the same analysis we did before, is equal to VR4 over R4, and that's equal to 4 volts divided by 10k ohms. And I know that that's going to be 400 microamps, but let's just prove it to ourselves. Here's 4 volts divided by 10 EE3 equals 400, and that says 0.6, meaning 400 millionths or 400 microamps. So there's 400 microamperes. Okay, and then we have IR5 is equal to VR5 over R5. And again, it's a parallel circuit, so this 4 volts is the same as VR4, VR5, and VR6. Just like up here, this 4 volts was the same as VR2 and VR3. So now we have 4 volts divided by 15k ohms, and that's equal to 4 divided by 15 E3, or 10 to the third, and we get a big repeating number, so this one we're going to call 266.67 microamps. And then we'll say that's, I'm sorry, we're going to give that a little approximately sign there, okay? I rounded. IR6 is equal to VR6 over R6, and that's equal to 4 volts over 30k ohms. You know, because this is twice as big, that this is going to be half as much. And I can tell you right now that's going to be 133.33 microamps, but you know, let's do it right. So we'll clear this and we'll say 4 divided by 30 EE3 equals a syntax error. Okay. 4 divided by 30 EE3. I don't know what I did. But there it is. There's your 100. If you look at this thing, you can see it's 133.3333. Just continued to the minus 0.6 or microamperes. So we'll do that, and now let's add these up. Okay. And I'll tell you what I'll do. I shouldn't do this, you know, this violates all the precision rules and everything. But let's call this 400 microamps out here. So now I'm going to do 0 plus 7. Make these line up better. So this one's going to be 266.67 microamperes, and this one's going to be 400.00 microamperes. Now, 0. plus 7 is 7, plus 3 is 10, which is a 0, carry a 1. I got a 0, and a 1 and a 6 is a 7, and a 3 is a 0, carry a 1. And I got 7 and 3 is 0, carry a 1. I got 7 and 3 is 0 again, carry a 1. And I got 1 and 2 is 3, plus 1 is 3. I was getting away with it because these were zeros. 1 and 4 is 5, and 2 is 7, and 1 is 8. So we get to 800 microamperes, and we have satisfied our Kirchhoff's current law. So there's a combination circuit. You know, if you had a parallel circuit made up of series subsections, you would do a similar approach, except you would start finding the individual currents before you found the individual voltages. In ours, we found the total current, and then we found individual voltages. Well, if this were a parallel combination of a bunch of series circuits, you would know this total voltage, and you would know the voltage across each of the parallel sections, and each of those would be in series. So you'd know that you'd have 12 volts across those, and you'd start boiling down and getting your individual currents, and you'd check them with your total current and all that kind of stuff. So we can put the wraps on resistive circuits here. I will scan these and get them into you, and you'll have this lecture, obviously. So I think that takes care of some of our individual circuits. Okay. And we'll get back to this sort of thing. When we do when we do AC circuits, but I don't want to mess up what we're doing now. Well, I will make a very quick lecture following this about AC, and I'll probably show you with a simulation what AC looks like, and some of the things we can say about it. Okie doke. All right. We'll see you next time. Bye-bye. Yep.
I'm so sorry.
That's all right.
Did they hear?
I'm sure. I don't care.
Was it a class, or was it are you off the air?
I am.
Was it a class, or was it a tape recording?
Tape recording.
Ah, shoot.
Yeah, it's all right.
The dog comes sliding in from
Yeah.
what the heck is that horn ball flying back up? Okay, first I thought you were on the
No.